Okay, let's dive into this. Welcome to The Explainer. Today, we're taking the intimidating, often incredibly abstract world of mathematical theory and we're translating it directly into practical tools for machine learning. Look, if you've ever felt completely overwhelmed by the sheer volume of math you're supposed to know for data science, or if you're just looking for a more efficient, laser-focused way to grasp these concepts, you are in exactly the right place. We are going to strip away all the noise and look at the actual, concrete building blocks that make predictive algorithms possible.
In the preface of our source material, the author brings up a famous quote by Galileo, who poetically stated that mathematics is the language with which God wrote the universe. Now that's a beautiful thought, right? But when it comes to the actual day-to-day practice of machine learning, we need to be a little more grounded. That brings us to this highly practical quote from Noam Chomsky. He hits the nail on the head. He points out that regardless of your engineering field, the basic science is pretty much the same. The real trick is learning how to actually apply it. In machine learning, engineering a practical application isn't just some afterthought, it is absolutely everything. The math literally only matters when it helps us build models from data to predict outcomes.
So here is our roadmap for today. First, we'll cover the machine learning math problem. Second, an application-first approach. Third, we'll meet the building blocks. And finally, vectors, matrices, and operations.
Part 1. The Machine Learning Math Problem.
So here's the trap a lot of beginners fall into. The background required in linear algebra and optimization is just massive. And worse, most existing college courses aren't really tailored to machine learning. Because of this, practitioners often try to pick up the missing bits and pieces of math via osmosis. You know what I mean? They just stare at machine learning applications and kind of hope to absorb the math as they go along. But our source text argues this is a deeply unsatisfying and totally unsystematic approach. Focusing solely on the application gets in the way of actually learning the math in a way that you can generalize to new problems. You just end up with this disjointed bag of tricks instead of a solid, rock-hard foundation. To fix this, we're relying on a fantastic framework from Charu C. Agarwal. The author completely flips the traditional script. Instead of teaching generic linear algebra, he goes completely out of his way to teach linear algebra and optimization strictly through the lens of machine learning examples. It is a focused, problem-solving solution that ensures we only learn the aspects of the math that are highly relevant to our field. It completely eliminates that frustrating learning by osmosis phase.
Section 2. An application-first approach.
Now, what's really interesting about this is how we bridge the incredibly abstract definition of linear algebra with something deeply human. In pure math, linear algebra is the study of linear operations in vector spaces. Think of plotting Cartesian coordinates in 2 dimensions. But in machine learning, we take real human attributes, like a patient's age, their blood sugar, or inflammatory markers, and we map those directly into these multidimensional vector spaces. Suddenly, a human patient is a high-dimensional data point. By defining linear algebra this way, we establish a concrete boundary. We're using linear functions to extract patterns from these complex data points to predict things, like, say, a binary diagnosis of cancer.
Section 3. Meet the building blocks.
Okay, there is a clear, step-by-step mathematical hierarchy here. We start from a single dot of data, we move up to a line of data, and finally, we build up to a full mathematical grid. Understanding this progression from scalars to vectors to matrices is absolutely crucial to feeling in control of machine learning math.
Let's begin at the very bottom with the scalar. Scalars are simply individual numerical values. In most machine learning applications, these are drawn from the real domain. To ground this in a relatable medical context, so it doesn't just feel like abstract math, a scalar is just a single attribute. If you're looking at a patient's medical chart, the number representing their age is a scalar. The single number for their blood sugar level is a scalar. It is literally the smallest possible unit of data.
But as you probably know, a single number rarely gives us the whole picture. And that is exactly where vectors come in. If you group multiple scalars together, like compiling a patient's entire medical chart into a single list, you create a vector. Vectors are just arrays of these numerical values. Each individual number inside that array is referred to as a component, an entry, or a dimension. The total number of components is the vector's dimensionality. So a vector perfectly represents multiple attributes of one single entity.
And this example brilliantly illustrates the concept in practice. Imagine we're looking at an employee database. We have a person who is 25 years old, makes $30 an hour, and has 5 years of experience. Well, in a machine learning algorithm, this person is represented purely as the array of numbers 25, 30, 5. Boom! That's a 3-dimensional vector. It perfectly and cleanly captures the reality of a person's life and career in a format that a computer can instantly parse and analyze.
Which brings us to Section 4, Vectors, Matrices, and Operations.
So the crucial point here is, do not let the word matrix freak you out. A matrix is ultimately just a familiar, friendly spreadsheet. When we have a bunch of individuals, we just stack their vectors on top of each other to create a matrix. This matrix has n rows and d columns. The n represents the number of individuals, or data points, in our dataset. The d represents the dimensions, or the properties, we measured for each individual. Any specific piece of data can be found by just looking at its row and column index exactly like you would in Excel. It is just a rectangular grid of numbers. That's all it is.
Once our data is in this format, we get to the fun part. We can run operations on it. Let's demystify the math of vector addition. If you have two vectors of the exact same dimensionality, you simply add their corresponding components together. Imagine a retail application where vector X represents the sales volume of various products in store 1, and vector Y represents the sales volumes in store 2. To find the aggregate sales, you just add the first item of X to the first item of Y, the second to the second, and so on. It is incredibly straightforward, but when you apply this to massive data sets, it allows us to instantly aggregate thousands of variables simultaneously.
We can also easily scale our data using something called scalar multiplication. If you have a single scalar value, let's call it A, and you multiply it by a vector, you simply multiply every single component inside that vector by A. For instance, if your vector contains massive retail sales numbers in the millions, you might apply a scaling factor of 10 to the power of -6. This single operation simultaneously adjusts the entire vector, scaling massive sales volumes down to manageable fractions, but without losing any of the proportional relationships between the products. It's simple, it's clean, and it's highly efficient. So, we've seen how complex human lives and massive retail records are cleanly translated into simple scalars, vectors, and matrices. We've seen how straightforward operations can manipulate these structures. But all of this leaves us with a fascinating, pretty provocative question. If a single patient is just an array of numbers in a massive matrix, how exactly does a machine learning algorithm optimize millions of these arrays simultaneously to discover hidden relationships and actually predict the future? The secret sauce lies in the optimization phase, where we maximize the agreement between our mathematical models and the observed data. But that mathematical magic is a whole different beast for our next explainer. Just keep this foundation in mind, and you'll be more than ready to conquer it.